Okay, starting a new chapter today, work, energy, and power. Okay, work, energy, and power. So we start off with the first concept about work. Work done. So what is actually work done? Okay, it has a symbol W. Okay, the definition of work done is, it is the dot or scalar product between force and displacement of an object. Okay, so it's a dot product or a scalar product between force and displacement. Okay, so the formula for work done is W equal to F dot S, okay, or Fs cos theta. We know that dot product, okay, if dot, you must have cos theta, cosine, yeah. You just want to highlight this part, okay. If dot, you must use cosine, yeah, because we learned before about dot product and cross product. So like for example, later on you will learn about cross product. Okay, another example of cross product, which is like torque. Torque, it is the right. Okay. Okay. So if you look at last time we learned about dot and cross product. Dot product we use cosine theta. If cross product we use what? Yeah, like later chapter you learn about torque. Yeah, this is actually about torque. In later chapters. Yeah, rotational or rigid body. You're going to learn about torque. This example is using a cross product, R cross F. For this one, the formula will become FR sine theta. It is using sine. Okay, cross product. Yeah. So we can. This is a cross, or we can say it's a vector product. Cross or vector product, we use sine theta, but dot product we use cos theta. Okay, so what's the difference between dot product and cross product? Okay, what you can see is dot product, you will return a scalar quantity, like work done. You see, anyway, this between these two, this dot product and cross product, both of them are called multiplication of vectors. They are called multiplication of vectors. So multiply, yeah, no matter it's dot or cross, both of them are multiplication of vectors. So you look at like this force and displacement, both of them are vectors. Both of them are vectors. But for dot product, you will get a scalar quantity. Like work done is a scalar quantity. That's why you see this force and displacement, top there you have arrowhead, but work done no arrow, because it's a scalar quantity. That's why this dot product is also called a scalar product. Whereas for a cross product, it is called a vector product. It's called a vector product. Like you see this moment R is a vector, force is also a vector, but after you multiply between these two vectors, you get another vector torque. This one you get another vector torque. Okay, this is cross product. That's why cross product is called vector product, because the multiplication of these two vectors, you get another vector. But for dot product between multiplication between the force and displacement here, two vectors, multiplication of these two vectors, you get a scalar product, a scalar quantity instead of a vector quantity. You get a scalar quantity, work done. That's why work done is just a scalar quantity with no direction. Okay, it has no direction. Okay, and then about the unit. Okay, talking about the unit, work done, the unit is joule. Okay, we know it's joule, and or you can write joule or you can write Newton meter, because it is F times S. F is Newton, S is meter. Okay, and you further derive in the basic quantities. Newton meter can be derived as kilogram per meter square per second square. Okay, this is the unit, SI unit for work done. Now, going back to why dot product we use cosine theta. Why we use cosine theta? Okay, because let's look at this example. Here you see, this is the force. Yeah, you see this is the force F, and this is the displacement S. So it's between force and displacement. Okay, multiplication, work done is the multiplication between force and displacement. Now, how do we get this Fs cos theta? So you look at here. Actually, this force has two components. It has the component parallel to the displacement, which is F cos theta. Okay, and it also has the perpendicular component, which is F sin theta. F cos theta and F sin theta. Yeah, using this angle theta here to resolve this force into two components, the parallel component and the perpendicular component, okay, to displacement. So to calculate the work done, we are actually using, we throw off the F sin theta, we only use the F cos theta to multiply. So actually to get the work done, we use F cos theta, yeah, the component which is parallel to displacement, to multiply by the displacement. So actually we are using only this part. We are only using this part. You see that? So you look at here. Let me write it down for you. So dot product, yeah, dot product F dot with S. Actually, we are using the parallel component, which is F cosine theta, to multiply with the displacement. Yeah, this is the parallel component, the force which is parallel to displacement, to multiply by displacement. That's why we have this formula. Okay, this displacement we just put into the formula there. That's why we have Fs cos theta. Okay, that's why dot product use cosine theta. So what happened to the F sin theta? We just throw it off. Yeah, no use. We just use the parallel component to find the work done by this force. We just use the parallel component of the force multiplied by the displacement. Why we only use a parallel component to multiply by displacement? Yeah, because it is this F cos theta that brings about this displacement. F sin theta has nothing to do with the displacement, isn't it? Because this object is moving to the direction. Moving to which direction? It is moving to the right, isn't it? It's moving to the right. So it is F cos theta responsible for this motion, to bring the object move to the right. Yeah, F sin theta has nothing to do. That's why work done is only caused by F cos theta. Okay. Okay. But if you talking about torque, maybe I should bring in this. Talking about torque, cross product, torque, we use F sin theta. Why use F sin theta? It is the other way around. Yeah, we don't use the parallel component, but we use the perpendicular component, F sin theta, to multiply by the whatever vector. Yeah. So but for cross product, we use the perpendicular component to multiply. Okay. So that is the other way around. Yeah, for cross product. But for dot product, we always use the parallel component to multiply. Okay. So about the torque, I will explain this later in later chapters. Okay, now let's look how to apply this formula into various situations. Okay, now let's say we have okay, maybe hold on a second. Okay, now here we have several situations. Okay, yeah, several situations. Okay, so let's look at this first one. So now we have force and displacement here. This force, yeah. Okay. All right. Okay, so this force is 30 degree to the displacement. So now apply the work done, yeah, to find the work done. So work done is equal to F dot S. Okay, it is F dot displacement. Okay, so this is the pulling force or pushing force, yeah, whatever. So this is just a force, external force. This is the external force at 30 degree to the displacement. So we apply the formula Fs cos theta. Yeah, dot product is a cos, we use cosine theta. Yeah, dot product use cosine theta. So this one we just use the theta is actually, what is actually angle theta? Theta is actually angle between force and displacement. Theta is actually angle between force and displacement. So now the theta between force and displacement is 30 degree. So this one we use 30. That's it. Yeah, Fs cos 30. And if you calculate this one, this cos theta, you will get a positive value. You get a positive value. So for this one, this work done, you surely get a positive value. Yeah, the work done after you multiply, this work done is actually positive. About the sign positive and negative, I will talk in the later video. Yeah, what is mean by positive work done, what is mean by negative work done. It has some result to the kinetic energy of the block. Okay, but this one I reserve to the next video. Okay, about the positive work done and negative work done. Right now, I just want to tell you that why is the work done positive? Yeah, how do you get work done positive? It's all because of the angle. Like this one, angle cosine theta, cosine 30 degree. It is a small angle, less than, like you see here, the angle, if the theta is a small angle like 30 degree, between 0 and 90 degree, if you use calculator and calculate cos 30, you surely get positive value. But if the angle like 120 degree, it is a big angle between 90 to 180, and then you multiply, we use, we use cosine 120, we surely get a negative value. Just now cosine 30, you surely get a positive value. Yeah. Don't believe you use calculator and calculate. Cosine 30, you get a positive value. When the angle is very small, you get a positive value. But when the angle is a very big angle, more than 90 degree, cosine 100, like cosine 120, you surely get a negative value. That's why you get positive work done and negative work done. Okay, I will elaborate this more in the next video. Okay, so what I can say is here, cosine 30, you get a positive. That's why work done is positive. Now, how about this one? This one also, we use the same formula. Now, the pulling force is 120 degree to the displacement. So, again, we use the dot product for work done. So, we use cosine theta. This one is cosine 120. So, if the angle is 30 degree, we use cosine 30. If the angle is 120 between force and displacement, then we use cosine 120. Cosine 120, again, the angle is big. Yeah, if you press calculator, yeah, more than when the angle is more than 90 degree, you will get, yeah, don't believe you just use calculator and calculate cosine 120, you get a negative value. That's why your work done also become negative. Okay, you get a negative work done. And what does it mean by negative work done? I will explain in the next video. Okay, now how about if like this is just now is we use external force. All of these are external force. So the force we also use external force here. Okay, now how about normal force? Normal force also has its work done. This one is work done by external force. We write work done by external force, WF. Work done by external force, work done by external force. Now, how about work done by normal force? Work done by normal force is, we must write subscript Wn. Then we use between normal force and displacement. We use normal dot displacement. Normal dot displacement. The force now is normal force, so we use normal force. And then become N as cosine theta. This one, what is the angle between normal and displacement? Normal and displacement, if the angle is 90 degree, perpendicular, isn't it? The normal force is always 90 degree to the displacement. So this one we use cosine 90. So what is actually cosine 90? You press calculator, you surely get cosine 90 is 0. So that's why for work done against normal force, normally is 0. Okay, so it has 0 work done. So what I can say is why it has 0 work done, this normal force? Because this normal force, there has nothing to do. This is like the perpendicular component, you see, it's like the F sine theta. It's like F sine theta. F sine theta does not bring the object to move to the right. No, yeah, it just support it only. It has nothing to do with the displacement. It has no effect. We can say this perpendicular component. has no effect, has no effect towards what? Has no effect towards the displacement. Because it's perpendicular, has no effect. So when the angle is 90 degree, you have zero work done. Again, like how about work done by gravity? This is like we normally write gravitational force, we write Fg. Why we don't write as? Because we normally write it is as weight, isn't it? We normally write this as weight equal to mg. But this time we try to change it to gravitational force instead of weight. Actually this weight and gravitational force, they are the same thing, same thing. But we don't write as W, we write as Fg. Better. Why we write as Fg? Because now work done is also W, isn't it? Work done is also W. If we also write W for weight, we confuse ourselves. This W is for weight, this W is for work done. So it is like repetitive algebra, repetitive alphabet. So we try to change it to Fg instead, yeah. But they are the same thing. The gravitational force and the weight, they are the same thing. Okay, both of them equal to mg. Okay, now we want to calculate the work done by gravity. So work done by gravity is actually between the gravitational force and the displacement. So the formula, now we work done by gravity, we like this. Okay, work done by gravity, we use is the gravitational force, okay, dot with displacement, yeah, multiply between these two vector. So it is okay, Fg is actually mg, okay, mg. So we use mg, yeah, change the Fg to mg, multiply by the s, and then mg times s cosine. What's the angle between gravitational force and displacement? It is the same as the normal force. It is 90 degree for this case, yeah. Sometimes the gravity, the mg is not necessarily 90 degree to the displacement. Depend, maybe it's on inclined surface. Let's say on inclined surface, okay. Like you see, this object. This object, let's say for this one, the displacement going up. This one mg, okay. This one the gravitational force is still downwards. This Fg equal to mg. This one is not 90 degree, maybe it's 130 degree. So this one is cosine. This one will then use what? Cosine 130. Understand or not? This to find the work done. This one will become the mg is not 90 degree to displacement. So the work done, to find the work done, you use cosine 130 for this one, yeah, for inclined plane. For inclined plane, let me draw the inclined plane, yeah. Yeah, don't know what's the angle here. So this one is 130. But for this case, if the horizontal surface, the angle is 90 degree. The angle is 90 degree. So this is using cosine 90. Cosine 90 for this case. So cosine 90, again, you press calculator, you will get 0. Isn't it? 0. Cosine 90 0. That means this, for this one, gravitational force is perpendicular to displacement. Does it bring any effect to the displacement? Any effect to the displacement? No, because it has no effect on the displacement. This gravitational force doesn't bring the object to the right. No, it has no effect. Again, it has no. I can write over here again. It has no effect. Again, it has no effect towards the displacement because it's perpendicular. Perpendicular. So, alright. So what I can say, zero work done. Zero work done. Understand? Again, zero work done. Alright. No effect of displacement. 90 degree. Yeah. Zero work done. Work done by normal force is 0. Work done by gravitational force is 0. Now, how about the friction? Friction. Work done by friction. Let's calculate. So if friction, work done by friction, friction is using the friction dot with displacement. If work done by friction, then we use the frictional force dot with displacement. So friction as cosine. What's the angle between friction and displacement? They are parallel to each other but opposite direction, isn't it? Opposite direction. So the angle becomes what? The angle, if opposite yet parallel, they are parallel yet opposite. So the angle is actually 180. It's not 0. Yeah, it's not 0. Is 180. 180. So this cosine 180. You must write 180. Remember, the angle is between force and displacement. Understand or not? Angle is always between force and displacement. So this is cosine 180. So cosine 180, what do you get? If you press calculator cosine 180, it is equal to cosine. Let's press your calculator cosine 180. You get equal to -1. -1. So this one, you get because this is a big angle. Big angle, you should get negative value. That's why this work done again is negative work done. And what does it mean by negative work done? I will explain later on. Yeah, negative work done normally will slow down the object. In short, what I can say. Normally if you have a negative work done, it will slow down the object. It will slow down the kinetic energy of the object. Okay, but you have a positive work done. It will increase the kinetic energy of the object. Okay, I explained already the reason. Yeah, if you have positive work done, you see this force is almost the same direction with displacement. Of course, this force will make the object move faster and faster. Yeah, will increase the kinetic energy of the object. But if the force is like almost opposite to displacement, negative work done, usually slow down the object. This object will slowly slow down. Like this one, you see friction. Friction is totally opposite with displacement. Surely this friction will slow down the object, will decrease the kinetic energy. So when decrease the kinetic energy, normally you get a negative work done. Okay, so like this one, you see. It will slow down the object. It will decrease the kinetic energy. This object, under this force, this object will move slower and slower. Yeah, this force will actually slow down the object, will decrease the kinetic energy of this object. But if the force is almost same direction with the displacement, it will increase the kinetic energy of the object. Okay, so this friction is always cos 180. You get negative work done. Okay, so that's all for this how to apply this work done for various forces. We have external force. If external force, we use WF. The subscript is WF. If normal force, we use WN. The force also use normal force. If the gravitational force or the weight, we use work done by gravity or gravitational force to multiply by displacement. If friction, we use work done by friction. We use the frictional force to multiply by displacement. Okay, and remember the angle theta. The angle theta is always between this force and displacement. Yeah, force and displacement, force and displacement, force and displacement, force and displacement, and force and displacement. Yeah. Look at what type of force and compare with. We always compare with displacement. You see that when we want to find the angle theta, we always compare with displacement. That's why for this chapter, drawing the arrow displacement is very important. We always need to find out what is the direction of the displacement. So we need to draw the displacement to compare with the force. Understand? Okay, I will talk about this more later on in the problem videos. Now, look at how to get zero work done. Okay, how to get zero work done. So looking at this one, the first case is force equal to 0. You will get zero work done. Like for example, like you see this equation. If the force here is 0, of course you multiply anything with 0, you get 0. Zero work done. Like you see spacecraft traveling with constant velocity in space. We know that space is a vacuum, isn't it? Space is a vacuum. Yeah, nothing there. So to move with constant velocity, and space is a vacuum, that means it has no air friction, isn't it? It has no air friction. Yeah, it has no Just want to draw it. There's no air friction. There's no air friction at all. Okay, so no frictional force, and also you don't need any what? You don't need any external force to maintain the velocity. You don't need. That means the net force is 0. Because vacuum, no frictional force, no air friction. So you no need to have the engine force. You don't need to on your engine. Also the spacecraft can move with constant velocity. We don't need external force to maintain the constant velocity because it has no air friction. That means it doesn't have air friction backwards. So you don't need pushing force going forward. No need. So we can say the net force is 0. The net force 0. So 0 work done. Understand? So how about the second example is displacement 0. We know that if the displacement is 0, also multiply, you get 0 work done. Okay, like you're pushing a wall, there is force exerted. No matter how hard you push the wall, but if the wall doesn't move, okay, doesn't move an inch, that means you do 0 work. 0 work. Okay, displacement 0. And about the angle 90, if the force and displacement is 90 degree, like this case, the theta is 90. All right, 1 second. Okay, like you look at this one, like you look at here, this theta is 90 degrees, isn't it? 90 degree between the force and displacement. The force and displacement is perpendicular. Like this centripetal force, you will learn in the next chapter about in the circular motion. Okay, circular motion chapter, you will learn about centripetal force. This centripetal force is always perpendicular to the velocity or perpendicular to the displacement. So this one actually you get Fs cos 90. Cos 90 is always equal to 0. So also you get 0 work done. So if this is how to get 0 work done. Okay, let me write something here. Okay, let me look at here. So if the force and displacement perpendicular to each other, like this centripetal force always directed to the center of circle. It is always perpendicular to displacement. So the work done by this what you call the centripetal force, normally centripetal force, the symbol for centripetal force is Fc. Is Fc, yeah? Centripetal force. You will learn in the chapter circular motion. Centripetal force, I should write this here, Fc, yeah? Fc. And the work done by centripetal force is always 0 because the centripetal force, this is the centripetal force, yeah? Because the centripetal force is always 90 degree to the displacement. And so cos 90, when the force and displacement perpendicular to each other, the work done is 0. Like for example, another like this example I told you about the normal force and the gravitational force for horizontal surface. The work done by gravity, work done by the normal force is 0 because cos 90, yeah, because perpendicular, the normal and displacement, they are perpendicular. So that's why this normal force has no effect towards the displacement. 0 work done. This gravity also 90 degree. So work done also 0 because there's no effect towards the displacement. The perpendicular force always has nothing to do with the displacement, has no effect towards the displacement. Okay, like this one, it has effect towards the displacement. Yeah, this one make it faster. But if the force is almost like opposite to the displacement, it will slow down the object. So when the force is not perpendicular like this, it has effect. This one, when perpendicular, it has no effect towards displacement. Yeah, it will not slow down. It will not make the object move faster. Yeah, when 90 degree, the force we cannot make the object move faster or move slower. So it has no effect towards the velocity or kinetic energy. Yeah. So when force and displacement, they are perpendicular to each other, no work done. Okay, so I think that's all for so 3 cases how the work done can be 0, force 0, displacement 0, or theta 90 degree. okay, perpendicular. So that's all for this part. Okay, thank you.